Hello, welcome back to another lecture of Phys 3500, Classical Mechanics. I'm your instructor, Dr. TJ Hammond. Today we'll be continuing on with another lecture on Chapter 7, Hamilton's Principle, Lagrangian and Hamiltonian Dynamics. So as I've mentioned before, we're developing the theory for Lagrangian mechanics to find a new way of solving mechanics problems. So as I said, you already know Newtonian mechanics quite well. You know that you can solve, a lot of these dynamical problems, but it turns out it's not always the easiest way to solve some of these problems. And there are some benefits to coming up with a different formalism. So instead of forces and momenta, we're going to look at energies and symmetry to solve our equations of motion. This week we're going to be finishing up the first 5 sections, so 7.1 to 7.5 is what we're covering this week. Your daily assignment will be compare the Euler equation to the Euler-Lagrange equation that we've been doing this week. So the Euler equation from chapter 6 to the Euler-Lagrange equation, which is what we've been working with this week. Compare this functional J from chapter 6 to the action S. And the answer for that is basically given on this slide, but I want you to fully appreciate what this answer is. Okay? So I'll let you go through that. So this lecture is actually going to be very short because basically we've now come to the fact that we've seen Lagrangian multipliers. We've seen Lagrangian multipliers in chapter 6. We've also now seen them for dynamics. We now just want to apply these things. So basically, for this lecture, for this tutorial and this lecture both, we're just going to be going through these examples. So we can start off with very simple examples where we have like a disk rolling without slipping. We had set this up in chapter 6 for understanding Lagrange multipliers. Now we're actually going to solve it. We also have this problem that we looked at last year in Phys 2500 where we have some mass on a hill. I think I gave it to you on a midterm where you had some ball or a hoop or a disc that's rolling on this hill and you had to calculate when it would fall off. Now we're going to just have it as a mass. This problem actually turns out to be far more complicated using Lagrangian mechanics, but you can solve it with Lagrangian mechanics and Lagrange multipliers. We'll also be looking at having a disk that rolls in this hemisphere, and we'll find the equations of motion for this. Now, this is going to be an interesting problem because we'll have this particle moving in something that's kind of like Cartesian coordinates, but it turns out that we'll be using these generalized coordinates to find this, and we can use this to find the equations of motion. This will emphasize these generalized coordinates. And our last problem is something similar to the first problem that we had, this rolling disk. So we have this rolling disk, but now what we have is a mass that's attached to a string here, and this thing can oscillate around as this thing is rolling down. So of course, as this thing accelerates, that's going to make this thing swing, but then that thing swinging is going to have is going to slow down this mass, and then as it swings forward, it's going to accelerate this mass. And so this is really, really complicated to do with Newtonian mechanics, but with Lagrangian mechanics, this is far more straightforward. So that's it for this lecture. So nice and quick, but we'll be covering these examples in class and lecture.